Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we will use WellFlo to model a skin reduction, partial penetration or limited entry skin reduction by perforation addition. So this is the fourth case. All right, we have discussed three wells and all of them showed that the productivity index will improve if we add perforation. The PI productivity index will be improved because the limited entry skin will be reduced when we add the perforation interval. Okay, so let's check. This is our model. You can see we have ESP here, all right, with reservoir pressure 800 psia, and then the current IPR model Vogel, and then productivity index, absolute open flow, all right. Flow correlations, we will use Duns and Rose, okay, and well and riser L factor 1.12. Reference depth, it is an onshore well, zero depth at Kelly bushing, and the distance between Kelly bushing to the wellhead is 17.39 in feet. And then we go to fluid parameters. So you see the oil API gravity is 36 or specific gravity of 0.8448 and gas specific gravity zero point 0.7, water salinity 12,000. No inorganics. All right. You can also open the PVT data calculator. And if you press calculate, you will get the bubble point pressure, oil formation volume factor, oil viscosity, and other fluid parameters. And you can also check the chart here. If you change the chart type to oil viscosity, for example, it will be like this, the plot of oil viscosity. Okay, and let's check the deviation first. All right, let's wait for a while. Okay, so this is the wellbore deviation. We have a deviated well with angle more or less 41 degrees at the bottom of the well, and equipment. We have tubing down to 3033 feet, and the outer or external diameter of the tubing, internal diameter of the tubing, and the casing. We have the casing down to 3,380 feet. Okay, let's now check the reservoir section. All right, so the reservoir is called B reservoir, and this is the pressure, and then the temperature, middle perforation 3,158, permeability. All right, and then the thickness, wellbore radius 0.4, water cut 0.95, gas oil ratio 300. Okay, and then the IPR model currently using Vogel with Vogel coefficient of 0.2. All right, but yeah, this is analytical model for the IPR, but I want to change it to IPR based on well test. Okay, IPR based on well test, and we will calculate the productivity index and absolute open flow. All right, so first I want to change the reservoir pressure 1000 psia. and the temperature 180 degrees Fahrenheit, middle perforation 3158, and then the water cut 0.95, all right, and then the gas oil ratio 300. I'm going to update the water cut to 96%, and then here for the well test data, I have the data for the pump intake pressure. Okay, and the pump intake pressure is 788. Sorry, the pump intake pressure 766.7. All right, and it will be converted to the bottom hole flowing pressure here. And the flow rate is, let me input, 2,351. Okay, so let's apply. All right, so if we input the pump intake pressure of 766.7, the calculated bottom hole flowing pressure is 810. And with the given flow rate, we get productivity index of 13.56 or more or less 14 stock tank barrel per day per PSI. And the absolute open flow is 7,423 stock tank barrel per day. Okay, you can use this productivity index. Let's say if you want to change to manual, you can just directly input the productivity index to 13.56 like this, and you will get the same absolute open flow. Okay, so I'm going to save this section, apply, and then save, file, save. Okay, now we will model skin reduction. Okay, we will model skin reduction, but you already know based on the previous videos, we cannot model skin reduction using using IPR based on well tests or IPR based on manual. We cannot because we don't have option for skin here. Yeah, maybe we have skin options here, but it is not comprehensive. It is only skin in by including non-Darcy effect. Okay, to better model skin reduction, you need to create IPR model based on analytical approach, or in WellFlow, we can do that in IPR using layer parameters. So if you go there, layer parameters like this one, okay, layer parameters like this one, you can model skin reduction by using this one. If you use calculated skin, you will have a new tab here, skin, and you have damaged skin, limited entry skin, deviation skin, and perforation skin. Okay, so by having the IPR using layer parameters, or its theoretical or analytical IPR, we can model skin. We can model skin reduction as well. Okay, so first I'm going to make a new model, okay, which mimic this real IPR, this actual IPR based on well test. Okay, so I'm going to create a new layer, okay, a new layer or a new model using IPR based on layer parameters, okay, by keeping the same properties like pressure, temperature, middle perforation, water cut, gas oil ratio, but I want to make sure that the productivity index is the same. So between the actual data, which is this one based on well test, and the model, analytical model that I want to create, they are the same. So when I want to simulate the skin reduction, I can do that in the new analytical model. Okay, so that's the game plan. Let me create a new layer here. and I want to call it matching. Okay, this is the model, analytical or theoretical model using matching, but not using test data, but layer parameters. Okay, layer parameters. And the pressure is the same, 1000, temperature 180, middle perforation 3158. Permeability, I want to check based on well lock, and then the same with thickness. Wellbore radius 0 0.4, relative injectivity no, because it is a producer. Water cut the same 0.96, gas oil ratio 300. And in the IPR model, we will model it with Vogel coefficient of 0 0.2, and then we will use calculated skin. Okay, and for analytical IPR, we need to define the drainage area geometry, and I will assume circular drainage shape with drainage radius based on rule of thumb 250, but you can also compute the drainage radius based on the cumulative production. Okay, here in my case, I will assume drainage radius of 250. So the drainage area will be calculated. By the way, for the DHC factor, for circular shape, it will be 31.6. But if you have another shape, you can just select like this one. Okay, if it is circular and using and you have water drive, it can be changed to like this one, 19.1. Okay, let's go maintain the base case, 31.6. Now I'm going to input the permeability and thickness. Okay, so based on petrophysical or log analysis, permeability is 497 with thickness of 100. Okay, and let's define the skin. Completion type, it's a case hole. So of course we will have damaged skin, but it is very difficult to model. We it's very difficult to know the damage zone permeability or damage zone thickness. Okay, maybe we can know if we perform laboratory testing, but yeah, on the field we cannot know that. And by the way, the damaged skin will be very small compared to limited entry skin. So yeah, just to avoid uncertainty, additional uncertainty, I will not include damaged skin. But I will include, of course, the limited entry skin, and nearest measured formation distance is 41.92. Vertical permeability, better if you have data from core analysis, but as a rule of thumb, it is more or less 10% of the horizontal permeability. So it is 10. Open interval 20 feet. Okay. So limited entry skin 20, right? 20, it's quite big. Damaged skin maybe 2 or maximum maybe 5, right? It is smaller than limited entry skin. So yeah, to avoid additional uncertainty, I will not include damaged skin, but of course I will include limited entry skin. And by workover, by additional perforation, I expect that the limited entry skin will be reduced. Deviation skin, we need to input the deviation. So if you go back to deviation, it will be around 41 degrees. Okay. And deviation angle, deviation skin, if you have deviated well, the skin will be negative. So it will give improvement in productivity index, but the magnitude is not big. Like you see right now, it's just minus 0.2. Okay. Perforation diameter, it is 0.37. Okay. And then this shot penetration in inch, 39.6. Shot density, 5 shot per foot. Shot facing 60 degrees. All right. And you see the perforation skin is 1.5. So you get productivity index of 30, giving you absolute open flow of 16.719. Let me save. Okay. All right. So you see here, the productivity index is 30.5, but based on well test data, if you go back to here, the actual IPR based on well test data, the productivity index is only 13.56. Okay, it's only 13.56. All right, so we need to do matching. We need to do adjustment so that the model, okay, so that the model here, if I go back to layer parameters, so that the model will give me 13.56 rather than currently 30.54. Okay, and I can do adjustment, but considering I don't have any certainty regarding damage skin, and I have quite high certainty regarding others, maybe I can adjust the permeability. Okay, maybe I can adjust the permeability to reduce the productivity index. Let's say, yeah, because permeability, horizontal permeability, what I use right now is log analysis result, and you know the investigation depth of the log analysis is quite shallow. It's only several inches, which of course will not cover all the flow area of the well. So permeability will have high certainty if you only use log analysis. Okay. Of course, you need to compare permeability based on log analysis and permeability based on well performance. And right now, we are currently doing that. Okay, I want to assess the permeability from log analysis. I want to assess and compare it with permeability based on well performance or well test data. Okay, and yeah, as you can see, it is currently not matched because permeability based on well log gives me productivity index of 30.6, 30.5, but permeability based on well performance give me productivity index of only 13.56. Okay, so let me change the permeability, let's say to 200. And you see productivity index reduces to 15.08. But of course, I need to change the skin as well. If the permeability is 200, so the skin in vertical permeability is 10% of 200. Okay, it is, oh wait, sorry. The permeability is 497. So the here in vertical permeability, it should be 49.7. Oh, the productivity index is even bigger, 57.5. Okay, so let's reduce the permeability to get the same productivity index of 13.56. So let's say 200, and let's change the vertical permeability to 20. Now it's 23. Change again to 150, 15 millidarcies. So it's now It's now 17.35. Let's reduce it to 120 millidarcies. All right, it's 12. Almost there. Now it's 13.9. Let's reduce to 115, 11.5. Okay, let me increase a little bit. 118. Okay, and then it is 11.8. Now it's 13.6. I want to, okay, change it to 117, 11.7. Now it's 13.5, right? So that's the way I will do the matching. So now with analytical IPR, theoretical IPR using layer parameters, by adjusting the permeability and setting all the parameters, we obtain productivity index of 13.53, which is very close to the IPR or productivity index based on well test, right? So right now we will model, we will create a new model assuming skin reduction due to perforation addition by workover, all right? Okay, so now the representative permeability is 117 and the absolute open flow is 7,400. Okay, so let's create a new layer. Okay, add layer, and I will call it after job or post job. Okay, and we will populate the data with the data that we get from matching. So pressure 1000, temperature 180 degrees Fahrenheit, and I will keep it, I will keep the middle perforation. I will change it later. Permeability 117, thickness 100, weld radius 0.4, water cut 0.96, gas oil ratio 300, IPR model Vogel, coefficient 0.2, and the drainage area geometry 250 meters, and the DHF factor 31.6, assuming circular drainage area. And go back to general, use calculated skin. Now let's go to skin, case hole, limited entry. Now after additional perforation, okay, let me check for a while. The middle perforation is shifted up to 3,114. Okay, so I will add perforation at the upper side of the current perforation. Go back to skin. Nearest measured formation distance now is 25 feet. Okay. And then vertical permeability 11.7. Open interval now it's 60. Previously only 20. So I will add 40 feet. Okay, in my perforation interval. So now the limited entry skin will be reduced significantly to only 3, which is very good, right? Which is very good. Deviation skin, 41 degrees. So the deviation skin will be minus 0.33, perf diameter 0.37, shot penetration, okay, 39.6, shot density 5, shot facing 60. All right. So now you see my productivity index, okay, productivity index increased to 24.8 stock tank barrel per day per PSI, and my absolute open flow increased to 13,570 stock tank barrel per day. All right, so previously, before workover, before perforation addition, the productivity index is only 13.56 or 13.6. Now, after I add the perforation, after I do the workover by perforation addition, now I can increase the productivity index from 13.6 to 24.8. All right. And as you can see, the limited entry skin decreased significantly. Previously, let's check the previous skin. Previously, it is 23. All right. 23. And the productivity index is 13.5. The absolute open flow only 7,400. And you can see here, nearest measured formation distance, 41, all right? And then again, limited entry skin, 23, open interval only 20 feet. Now, after I add the perforation, okay, I shift up the middle perforation. I make the formation distance closer to the perforation, or I make the perforation closer to the formation boundary, reservoir boundary, only 25 feet right now. Limited entry skin reduced significantly from 23, now it's 5.6. And again, productivity index increased significantly from 13.5 to 24.8. Okay, so right now I will save the model and I want to create the show composite IPR. Okay, show composite IPR currently have problem because if we go back to the actual IPR based on well test, okay, let's check the data. Okay, by the way, here it should be 117, thickness 100, and the skin is 41.92, 11.7. Let's make it the same with matching. Open interval 20. Okay, well deviation 41. Perf diameter 0.37. Shot penetration in inch 39.6. Shot density 5. Shot facing 60. So it's the same with the matching IPR here, the same. All right. Now let's create the composite IPR. Here, show composite IPR. Plot. All right. There. And if we show the legend here, so the blue one, it's a composite IPR assuming that you total all the layers. But actually, they are not three different layers. They are the same layer, but with several scenario. One is with IPR based on well test. The second one is analytical IPR. And the third one is the same layer, but with perforation addition. So there is no necessary to plot the blue one because actually we cannot add the layers. They are the same layers, but with different model. So I will make this one white color to avoid misunderstanding. And then here on the horizontal axis, let's change it to, let's change the maximum to 15,000. Apply. Okay. So you see this one, the orange IPR is IPR post job. IPR after the perforation addition, after the workover. So you can see we have improved productivity index. We have bigger IPR after the job because we add the perforation, we decrease the skin. And this one, the red one, is IPR before the job, but created using analytical IPR. It is perfectly overlaid with this one, the green IPR. Okay, the green IPR is model based on well tests. Okay, they are perfectly aligned, so you cannot see the green IPR because the green IPR will be the same with matching Vogel IPR, the red IPR. Okay, so again, by adding the perforation, I decrease the limited entry skin and I increase the productivity index, I increase the IPR, I increase the absolute open flow or maximum flow rate. All right, so that's the thing. If you want to increase the productivity index of your well, you can do stimulation like acidizing or hydraulic fracturing, but you can also do perforation addition. All right, so that's all. I hope you enjoyed the video. I hope the video is useful. Thank you so much for watching and see you again in the next WellFlow videos. Thank you.